They said Moore's law was dead. Not once, not twice, but more than 20 times. Yet here, at Stanford University, in the beating heart of Silicon Valley where it all began, the spirit of Moore's law still breathes, defiant, evolving, and very much alive. The story of modern civilization is the story of the transistor, a device so small it can switch billions of times per second, yet so powerful it built our entire digital world. From the phone in your hand to the AI that writes poetry, everything depends on that microscopic miracle. But today, that miracle stands on the edge of reinvention. For 50 years, technology has raced forward, fueled by one equation: the number of transistors on a chip doubles roughly every 2 years. That rhythm of progress became the heartbeat of modern computing. Inside every chip, these transistors act like microscopic light switches, billions of them turning on and off in unison, powering everything from your smartphone to ChatGPT. Yet something remarkable is happening. Every tech giant, from NVIDIA and Google to Apple, has entered the same secret race, not for bigger screens or faster networks, but for the ultimate chip. Because whoever controls the chip controls the future. Look closely at NVIDIA. Their latest Blackwell GPU holds 28 billion transistors. That's 28 billion switches working together every nanosecond. But the next generation, the Rubin platform, is set to redefine what's possible: 1.3 quadrillion transistors within a single computing system. That's not science fiction. That's happening now. Yet, here's the paradox. While AI capabilities double roughly every 7 months, the hardware, the very silicon it runs on, only improves by 1.4x per year. This gap is growing wider every day. And to understand why, we need to look deeper, beneath the glass and metal, into the quantum pulse of the transistor itself. Innovation in chips doesn't happen at one level. It cascades through layers. At the device level, engineers reinvent how electrons move. At the architecture level, designers create new ways for circuits to compute. At the system level, companies optimize everything, from software stacks to cooling systems. Yet, at the foundation of it all lies one word: transistor. Most people know TSMC, the global titan that manufactures chips for the world. But behind the scenes, another institution shapes the future: IMEC, a quiet powerhouse of innovation based in Belgium. IMEC invents the next-generation transistor technologies. TSMC then builds them for everyone else. And recently, IMEC revealed something extraordinary: a roadmap that stretches nearly 2 decades into the future, mapping how humanity will shrink from today's 2-nanometer chips to a breathtaking 0.2 nanometer frontier by 2037, and even beyond 2039. It's a blueprint for the next age of computing. Rewind a few decades. Back then, chips used planar transistors, simple, flat, two-dimensional structures. A transistor is, at its core, a gate. Apply voltage and current flows from source to drain. Engineers kept shrinking these channels, the tiny pathways where current travels, until physics itself rebelled. To go smaller, they had to rethink the shape of reality. So they flipped the transistor upright, like a fin slicing through water. This new 3D structure became known as FinFET, short for Fin Field Effect Transistor. It offered better control, lower leakage, and the ability to pack more transistors in the same space. At that time, the industry was ecstatic. The FinFET era began. But like every champion, FinFET had its limits. The faster we ran, the more we hit the walls of physics, and so a new hero was born. Today, as we stand in 2025, we are witnessing the next great transformation: the shift from FinFET to gate-all-around, or GAA transistors. Imagine laying that vertical fin on its side, then stacking several layers like a futuristic skyscraper made of atomic floors. This new design wraps the transistor's gate around all 4 sides of the channel, allowing unprecedented control over the flow of current. More control means smaller, faster, cooler chips. TSMC plans to bring this technology into Apple and AMD chips by the end of this year. The engineering behind it is breathtaking. The underside of these nanosheets can't even be seen directly during manufacturing. Only specialized machines from Applied Materials and ASM can handle it, using techniques guarded like national secrets. The result? At the N3 node, TSMC could pack 200 million transistors per square millimeter. With N2, 2nm, they reached 300 million. Numbers that were unthinkable just a decade ago. But the real revolution is in how chips are powered. For decades, all the wiring for power and signals sat on top. Imagine trying to fit all plumbing and electricity through your ceiling. Now, engineers are flipping that entire system. Backside power delivery. All the power lines go beneath the chip, freeing the surface for logic and data pathways. It's elegant, efficient, and revolutionary, but also incredibly complex. Intel and TSMC are locked in a race to perfect it. And from next year, this architecture will power everything, from smartphones to AI supercomputers. According to IMEC's roadmap, we will push this architecture to around 1 nanometers, or roughly 10 angstroms. Beyond that, the old methods will break down. To move forward, we must reinvent again. Enter CFET, complementary field effect transistor, the next leap. Think of stacking not just wires or sheets, but entire transistors, one on top of the other, vertically. Like skyscrapers rising higher as cities run out of land. CFET will open the door to single angstrom dimensions, the true atomic scale. Beyond architecture, another frontier awaits: materials. For decades, progress relied on better designs and lithography tools, but still on the same material, silicon. Now, the next era belongs to 2D materials. Substances only 1 atom thick. 2 names dominate the race: molybdenum disulfide, MOS2, and tungsten disulfide, WS2. These materials could replace silicon entirely, but they are devilishly hard to manufacture. Their thinness makes them fragile. Even a microscopic misalignment can destroy them. Imagine building a skyscraper out of dust grains, aligning each one with angstrom precision, without ever touching them. That's what modern chip fabrication demands. To print features this small, the industry turned to light itself. Lithography, or litho, as engineers call it, is the process of carving microscopic patterns onto silicon wafers. Over time, metal lines, the interconnects that carry signals, have shrunk from 40nm pitch to 20nm, and soon beyond. To get there, the world's most complex machine was built: the High-NA EUV lithography system by ASML. Its 0.55 numerical aperture gives it unmatched resolution, allowing it to etch atomic-scale features. And it works. This tool has eliminated lithography as a bottleneck. It's now the core enabler of sub-2 nm manufacturing. But even this won't last forever. Beyond 0.55 NA, a new class is coming: hyper-extreme EUV, or hyper-EUV, the next frontier in light itself. This will usher in 2D FET, a new device type where the transistor's channel is made entirely of 2D materials. It will be the ultimate convergence: architecture, material, and light, all working in harmony. Further down the roadmap lies another contender: carbon nanotubes, or CNTs. Essentially, they are rolled-up sheets of graphene, the most famous 2D material on Earth. Graphene is incredibly fast and efficient, operating at lower voltages, sometimes below 0.5 volts, potentially reducing power consumption dramatically. But there's a problem. CNTs leak current when idle. They're great at turning on, terrible at turning off. Still, researchers believe we'll first see them used selectively in hybrid chips, where different layers perform different functions. This vision is called CMOS 2.0, a layered chip sandwich where each layer specializes. One for AI, one for graphics, one for logic. As compute performance skyrockets, memory has become the new bottleneck. Modern systems rely on a trio: SRAM for cache, DRAM for active memory, and a NAND for storage. The problem? SRAM, built from transistors, no longer scales efficiently. At 3nm and 2nm, logic keeps shrinking, but memory lags behind, devouring more chip area. The CFET architecture, with its vertical stacking, may finally offer salvation, allowing denser SRAM layouts without sacrificing performance. Meanwhile, DRAM has gone vertical too, stacking layer upon layer in 3D. But even then, a deeper issue remains. The memory wall. The growing delay between fast processors and slower memory systems. As AI grows, this imbalance threatens to slow everything down. Solving it will define the next decade of computing. As technology grows more complex, so does its cost. While each transistor may stay roughly affordable thanks to higher density, the cost of an entire wafer skyrockets due to extreme manufacturing complexity. This is why competition is vital. Intel, TSMC, and Samsung are all investing billions in advanced fabrication to stay in the race. Without that rivalry, progress could stall. For consumers, it means prices of high-end devices and AI services may rise. But for investors, complexity means opportunity. The semiconductor industry remains one of the fastest-growing and most strategic fields on Earth. If you're watching the markets, three names matter most. TSMC, the master manufacturer, ASML, the only company building EUV lithography tools, and Applied Materials, the quiet backbone, supplying tools used in every fabrication step. And at the center of it all, IMEC, the silent architect of tomorrow. Moore's law isn't dead. It's being reborn, through reinvention, through material science, and through human ingenuity. The transistor has evolved from flat to fin, from fin to nanosheet, and soon from nanosheet to stack. It's a journey from silicon to the very edges of quantum matter. And while the challenges ahead are immense, alignment at the atomic scale, manufacturing at impossible precision, the rewards are transformative. This is the quantum silk route, where technology, power, and destiny intersect. Subscribe now and travel with us into the future. We are approaching a world where computing becomes invisible, omnipresent, and almost alive. From the smallest chip in your smartwatch to the massive GPU clusters powering artificial intelligence, the entire digital universe rests upon this invisible evolution. By 2039, humanity may master angstrom-level chips, 2D materials, and stacked architectures, an era where silicon itself becomes history. But one truth remains timeless. Progress never stops. The transistor, that tiny switch of charge and spin, continues to shape the destiny of nations, industries, and people. And as Moore's law evolves from prophecy to persistence, the question is no longer whether it lives, but how far it can still take us. The story of transistors is the story of human ambition, and this is only the beginning.